Hi, we're finishing up Lesson 8 with looking at residuals for simple linear regression and some other issues. So we're going to calculate residuals, we're going to determine was it appropriate to fit a line, and talk about extrapolation and outliers. So a residual, it's going to be the difference between what was actually observed and what was predicted by the line. So the number of residuals is going to equal the number of observations in your data set. So for my high school example, I had 10 students, so I'll have 10 residuals. And I am just taking, so here is the predicted, what the line predicted, a 3.6 high school GPA student would have in college. And here's this point, that's what we actually observed. We have to take that distance. So y is what was observed minus y hat minus what was predicted by the line. So why are they important? We use these residuals to actually calculate the line. We find the line that minimizes all the residuals simultaneously at once. So whatever can make those distances the smallest at once. And it can help us assess how the line fits, if the line is an appropriate model for these data. Because if these data don't have a linear relationship, we don't want to be fitting a line. So why are they important? I'm going to throw out this example. And this might be an example where it really is important to pay attention to the scale of your axes. So we have here college students, number of credits they're enrolled in. I feel sorry for these folks up top. I did that like one semester, and that was it for me. And their exam score on their first midterm. So looking here, we want to know, maybe is it fair to make a line? Maybe. It's hard to tell. Especially since we have this 0 through 100 scale, but almost everything is between 60 and 80. It would be a lot more useful if it were zoomed in. So we go ahead, we fit a line, and look at the residuals. So even though it looked linear on that last slide because of the zoom, residuals really kind of amplify the relationship that's going on. I see a big curved relationship. This tells me, nope, we were wrong to fit a line. We actually needed to fit a curve. That kind of idea. So it may not have been obvious just looking at the scatter plot of the two variables, but once you get the residual plot, you can see that curved relationship and say, oh, no, it wasn't appropriate to fit a line. So calculating the residual, so we're going to stick with our high school GPA example. So we have a student that had a 3.6 in high school and a 3.3 at the end of their first year of college. And we want to find the residual for that student. So this right here, we're trying to find this distance. So y is what was actually observed. It's right here. So it's that 3.3. So they actually had a 3.3. Y hat, that's when we plug the 3.6 in there. So at 3.6, we did this a few slides ago for making a prediction. So I'm actually going to write it this way. Do the multiplication first. You end up getting 3.498. So your residual, it's what you observed. So y minus what you predicted. So y hat. So 3.3 minus 3.498. I'm going to get negative 0.198. So this is my residual right here. So looking here, here's my residuals plot. If I look here, here's my high school GPA, and this would line up with about negative 1.98. It's going to be really, really close to that negative 0.2. So just illustrating there. That's my residual. So residual plot. Here is our residual plot for the GPA example. It's a scatter plot of all the residuals for it. So however many observations you have is how many residuals you have. So what you put on this axis, it could be your explanatory variable, your response variable, an ordered index. It doesn't really matter what it is that you put on this particular axis most of the time. On the y-axis, it's your residuals. So that 3.6, it lines up to that negative 0.198, that kind of idea. And we use this to assess how well our line is doing. One, was it appropriate to fit a line? And then we have conditions for inference. So we have conditions that we have to meet in order to use this line to make good predictions. In general, we want random scatter around 0. So they should be centered around 0, and you should have roughly even, no obvious pattern scatter. There is an outlier out here, but that's that student we pointed out earlier. They had a 3.3 in high school, and they had a 3.6 in college, so it was a bit higher than the line predicted. So remember, this is x, this is y, this is y hat, and this is y minus y hat. So now assessing this to figure out, hey, should we be able to use this line to make predictions? If the conditions are met, we shouldn't see any obvious patterns, and it should be roughly scattered around 0. Because on average, if the line is doing really well, they shouldn't have big differences from 0. They should be close to the line. The bigger the residuals, the further from the line the points are. So here's my scatter plot. If I want to make the residuals plot. So looking here, this is kind of nice and even. No obvious patterns. The spread is pretty consistent throughout. It looks good. So no violations means go ahead, use this line to make predictions. You're good. However, sometimes we can violate these conditions. So suppose I have this scatter plot and I fit a line, and it doesn't look too bad. But then I go ahead and I get the residuals plot, and I have this big fat curve in there. Looking here, I have violated, I fit a line when I should have fit a curve. So this is a linearity violated. So it means I fit a line when the relationship wasn't linear. So then our second scenario, looking here, I fit a line, then I get my constant variance. Then for my second scatter plot here, I fit a line, and then I get my residuals plot, and I don't have nice even spread, right? It gets bigger and bigger. It fans out. If that spread changes, so it goes from little to bigger and bigger, this fanning out is a violation. So no constant variance. Because one of the ideas is the spread around this line needs to be roughly the same. Because if not, our predictions down here are a lot better than our predictions over here. You want the line to be consistently useful for making predictions. So that means the spread around the line has to be roughly the same. But in this second example, it is not. So that'll be a problem. So warning when we see this type of pattern. So if you see, fanning out or funneling in at all, or repeated, like you can see them both, you should worry about constant variance. If you see a curve, you should worry about linearity. And if you violate either of these, then it's a concern that you shouldn't be relying on your least squares regression line to make predictions, your line is not going to be reliable. So back to our GPA example, based on the residuals plot, are they met? Oops. So yeah, we do have this outlier, but I would argue, it's roughly evenly spread, and it's centered right around 0, and there's not a big obvious curve in here, so I'd say yes. Roughly random scatter, no obvious patterns. This is our happy place for residual plots. We don't want there to be patterns. The second you're spotting patterns, it usually means something's violated. So conditions met. I would say yes, I'm satisfied that they're met here. That go ahead and use our line. But once again, 10 students is not a lot. You'd probably in reality use a bigger sample size than 10. So I'll give y'all a second on this. Based on this residual plot, do we think they're met? Okay, so hopefully y'all spot it. First off, they don't look very centered around 0. We have a couple of really big ones, outlier type points, but there's definitely a huge curve shape. So no, violated linearity assumption. We fit a line and the data were curved. So linearity condition assumption mean the same thing here. And in general, as long as you violate one of them, that's enough. So you could go on about constant variance, but really if one of them's obviously violated, just talk about that one. That will be enough most of the time. So then other issues, extrapolation. I cannot tell you how many times I hear this a lot in TV shows. Like I was watching that TV show Bones, and they proudly talk about extrapolating all the time, and it's like a swear word a little bit in stats. So keep it in mind. It's not always a great thing. So extrapolation is when you make predictions for values of the explanatory that you didn't see, like that aren't even in the range of what you saw in the actual data set. Your line that you made really only represents what happens for the range of values that you actually saw. And we'll have an example, a specific one. So for example, the GPA example, here I have it plotted, and you can see almost all the points, they're kind of between like 3.0 and 4.0, roughly. But suppose now I want to use my least squares regression line to predict the college GPA of a student at a high school GPA of 0.5. So here's 0.5. I go okay. Well, if you see here, this is so far outside of this range, this is extrapolating. If I go ahead and make predictions outside of there, I don't know that whatever goes on out here is still a line. It could be really curvy, it could do all sorts of crazy things, but I don't know. I only know what's going on right in here. So I only want to use GPAs between, I don't know, I think it's 3.1 and 4.0 roughly. I only want to use my line to make predictions for high school GPAs between that range that we actually observed. Definitely height is one that you see people do a lot, like when you have toddlers and whatnot, because the growth charts are something like this. So if you only look here, it's linear, but over here, the pattern changes. So you want to be careful. You don't want to make predictions for values outside of the range of what you actually observed. So yeah, could you plug it in? Yes. But it would be dangerous because we don't know that this relationship stays linear. So then one last thing we want to talk about, outliers. So outliers can be a problem. It does not mean you can just remove them if they are a problem. But first off, you can have an outlier and maybe it doesn't have an impact, or it does. So influential outliers, like this one, they change the line, like significantly. So without the outlier is this reddish line, and it kind of goes right here. But if you have the outlier in there, it changes to this black line. It pulls the line towards it. So towards that point. So an outlier will be influential if the line moves a lot when you remove the point. Versus you can have an outlier like this one, and it really doesn't influence that much. Yes, it shifted the line a tiny bit, but that slope is pretty much the same. It really didn't change the line that much. So you can kind of identify like where this would be almost. So influential outliers tend to be in the extremes, so they tend to be way on the left or way on the right. Non-influential outliers tend to be closer to the middle xy's. So yeah, the closer to the middle they are, the harder it is for them to influence where the line goes. So one thing that's really great about having large sample sizes is the bigger your sample size gets, the less of an impact your outliers are going to have. So unless and then it does say that unless you've identified like, hey, this outlier is an error, it doesn't belong in this data set, basically some non-statistical reason, it cannot be, oh, I don't like this point, you shouldn't remove a point unless you have a non-statistical reason. So that could be like, oh, we discovered, we have these athletes, and the coach participated, so we should remove the coach from the data set, or something like that. I have seen where, somebody, they measured this wrong, and we had to remove everything a certain investigator measured. Yeah, outliers, maybe they stink, but you really can't remove them without a really good valid reason why they don't belong in the data set. Must be more than I don't like them. So I believe that is going to be it for our lesson 8. And now these are your turn examples. So these slides are a great example. Like here, you try calculate the least squares regression line for this data set. This one says, okay, we'll estimate, the college GPA for high school GPA of 3.8. And what's great, after you finish these, they have video solutions so you can check your work. Great place to get some practice. Okay, I look forward to talking with y'all on the discussion boards.